The third type of process we're going to look at is an isobaric process, or one where the pressure doesn't change. We can say delta P is equal to 0. And so work in this case is going to be pretty straightforward. Remember, minus P external dV. And since the pressure is constant, we know that the system pressure and external pressure have to, by definition, be equal. Because if they're not equal, then the volume will be changing. Or if they're not equal, then there's an imbalance in the system, and so forces will be happening. But we're saying no, they have to be equal to each other. That's sort of by definition. Okay, so we can write that this will be minus P delta V. Right? There's nothing more to say to it than that, right? We can just integrate this and we just get minus P delta V. And P external and P system doesn't matter, they're the same thing. Okay, what about du? Well, U only depends on temperature, which we've established for an ideal gas, right? This is, for all these cases we're talking about, this is all ideal gas behavior. And so we can say that du is going to be equal to Cv dt. We can integrate that and say that delta U is equal to Cv delta T, just like we did previously. And so we can say we have a value for du, delta U. We have a value for W here. And so we can say that Cv delta T, again that's delta U, is equal to Q plus minus P delta V. And this is W. So we can rearrange this to find an expression for Q as well. So Q is equal to Cv delta T plus P times delta V. And that gives us an overall expression for all three of our parts of the first law. So isobaric, we can't get much more specific than this. So we kind of have two different things going on, different parts of it. There's the part that depends on temperature, and that's going to affect our internal energy. And there's the part that depends on the volume, and that's going to affect our work. And those are sort of the two possibilities that we have if we're considering just an ideal gas and a reversible process.